This conference will now be recorded.
Thank you, Kishore. Thank you for joining me this morning. So we were discussing about training the models and important aspects that is involved while training a model. And how do you first train a model, understand the errors, do the cross-validation, do the visualization, what is the difference between each of the model, and why you need to go with the one model, why not the other model, and there is no theory explained to tell you that yes, for this data set you only need to do this model. No, it was never the theory in data science and machine learning that for this kind of data you need to use this model. It was never written, it was never told. That is the reason why you need to be aware of each and every model such that it will be easy for you. If you know each and every model's implementation, the results, hypothesis, and the way it works. So we have been discussing about linear regression. We discussed about other areas of linear regression, how errors are calculated in linear regression, and we also talked about scotartic gradient descent, mini batch gradient descent, and batch gradient descent. Okay. Till this point, we made observations from each of the model and try to understand which one was best. If you look at the table in front of me, I have shown you what happens with normal equation, what happens with batch gradient descent, scotartic gradient descent, and mini batch gradient descent. Which one is large, which one is out of core, which one has more hyperparameters, which one requires scaling, and which one is supported scikit-learn. So if you have this knowledge, then while you are working on real-time projects or when you're working for a client, then you will be fast in decision making and you'll also work more comfortably. Okay, so if you don't connect the dots of the previous class and if you are not clear with the slide number 1 to slide number 53, that won't help you. Okay, for that reason I would request you to please kindly go back, revisit, and let me know. Let's go back to 54 now. Today we are talking about polynomial regression. What is polynomial regression? Now if you ask me about if I ask you about linear regression, you are in a good shape. Before I go to linear regression, let me show you something. This is the agenda. Okay, in this agenda we have successfully completed this bit, the normal equation, and the computational complexity you have a normal equation. On the linear regression we have explained. We spoke about gradient descent, we spoke about batch gradient descent, scotartic gradient descent, and mini batch gradient descent. Okay, today we are going to talk about polynomial regression, and we are covering a part of learning curves. When I say we are part of learning curves, we are not covering the regularized linear models. We are only covering this part. Okay. I think I'll have to finish this one by tomorrow, but looks like it will take some more time. Maybe by Saturday, I think I should be able to complete it. Okay. Now, understand the flow, what we are doing, why we are doing it, and what is the relationship and establishment of each of the topic. If you don't connect those dots, then you will not understand why we are going so deep into each and every topic. Perfect. Now let me go back to 54. Yeah, this is where we are. Guys, look at the diagram, understand the concept. This is all theoretical, and while we are understanding the concept, on the go, we are also doing the practicals. I am also attaching the screenshot of the results so you can compare the theory versus practical. Okay. Now, what is the polynomial regression? Y equal to x squared minus x minus 2 is shown in the diagram. And if you look at the slope of the red line starting from the top, it converges to the bottom, again went to the top. Now, so far, we have just looked at the data having a linear relationship or a straight line. When I say linear relationship, again, the line of graph, which is called y equal to mx plus c, and straight line is the one that explains you the actual prediction, actual data versus predicted data. Now, what if we have to fit nonlinear data by quadratic equation? This is a new term for you. What is the quadratic equation? Very simple. Quadratic equation is used as a part of linear algebra in machine learning. Okay. The way you use a normal equation when you are talking in linear regression, here you are talking about quadratic equation. The quadratic equation is the equation that makes the relationship of an data terms. Okay. Now, for example, if I have an features called A, B, and C, and if A not equal to 0, I'm just telling you for example, if A not equal to 0 or if A equal to 0, will the equation be linear and or if the equation be not quadratic? The linear relationship is like, if I increase this, will that increase? If I decrease this, if that is decreasing. That is the linear relationship. But in the form of quadratic equation, the way how it works is you will have to check in two ways. When I say two ways, with A not equal to 0, considering with A not equal to 0, and if A equal to 0, will the equation be linear? That is the important concept of it. Okay, then that's all it is. You don't have to worry much about it. It is quite simple. This is just a mathematical formula, guys. This is just a mathematical formula, and people will use it in different ways. Somebody will say y equal to ax square plus bx plus c, and somebody will say y equal to x square minus x minus 2. And these are the kind of things you need to know about quadratic equation. Basically, quadratic equations are used as in your daily life when you are calculating the areas, when you are trying to determine the product's profit or something like that. And this is simply a kind of equation. But what happens is, in this one, you will have at least one squared variable. Here you have x squared minus x minus 2. Later you may have a minus b squared minus c, or you may have a minus b minus c square or a plus b minus c square. It depends. Just remember that. Once again, do not confuse. The quadratic equation is nothing but like the way you have linear relationship between two features, like that in quadratic equation, you take one feature assumption as 0, and what happens if that is 0, and you check with a and c. And if I have a b and c, at first case I take a equal to 0 and see what happens with b and c. Second case I take a not equal to 0 and see what happens with b and c. In this situation, at least one of the variable will have a square. That's all you need to do. Now, here what happens is, clearly a straight line will never fit this data properly. Perfect. Because if when you are trying to find a quadratic equation or quadratic formula between two features, the straight line will never fit it. Because if the straight line is fit, then it says, boss, you guys are nowhere related. Don't just try to make out something within yourself. Now, then, when a straight line is not fitting the data properly, how do we fit this kind of nonlinear data? Question mark. Think. Think logically now. So if you have a linear relationship, that's a different story. But now you don't have a linear relationship and a straight line is never fitting the data properly. How do you do it? Now, when we want to fit this kind of nonlinear data, we have to use a linear model to fit nonlinear data. We add powers for each feature as new features and train a linear model on extended set of features. This is called polynomial regression. Now, there are three important points here. The first important point is you can use a linear model. The reason why you're using a linear model is a linear model to fit nonlinear data. Makes sense. Add powers of each feature as new features. Makes sense. Now, when I say add powers of each features as new features means adding or increasing the weights of the existing features so that they become new features. Now, train a linear model on extended set of features. Again, initially, simple was the way you can understand this. Initially, you have 10 features. Got it. Now, how can you fit a linear? I'm really sorry. I'm kind of getting this sneezing sensation and had to pause in between. I think I'm gonna catch a cold again. So, how do you? I'm repeating it again and again because if you understand this, the whole concept of today's discussion is understood. I have very clearly represented in diagrams also, so kindly focus. If I'm not making any sense to you, give me a shout. I'll change the direction of the approach. So polynomial regression is very nothing. You are guessing that there is no linear relationship. On that kind of data set, how are you going to fit the data properly? For that one, use the linear model for the nonlinear data. Awesome. Again, can you increase the weight or power of the features so the weight increased features are used as new features? The way how I can say this one is you are wearing a normal, you are just using a very normal car which is quite old and you're traveling from one place to other place, and now I have given you more weights such that your car is serviced properly. Your car has given high energy fuel, and the same car has serviced and properly maintained, properly reinvented. And what is the performance now? That's what it is, simple. So once your features are reinvented or once your features are added weights, then what you will do? On top of that, you will run the linear model. This is called polynomial regression. Can I please check if the slide is clear and move on to next slide quickly?
Yeah.
Perfect. That's good. Now, let's test the linear regression now. Polynomial regression. As of now, every regression I have explained you, I have implemented it practically. I have shown you the graph. I have shown you the relationship, and I also shown you the code and taken a screenshot of the implementation. So please kindly take your time, practice it. And if you practice also, if it's not making sense to you, I can do a whiteboard session, explain everything clearly. Now, okay, so to do, we have discussed three important points. First thing, we are going to deal with nonlinear data and we are going to fit a linear model to the nonlinear data. We are going to add more features or we are going to add more powers to the existing features and we treat them as a new features and we fit a linear model on top of that data. Now, To do that, what should I know? I first need to generate some nonlinear data. Now, how can I do that? Based on the quadratic equation. Now, plus some noise. Guys, when I say noise, noise means random data. Always remember, I have been using this term so well. I thought to highlight this one, but I wanted to highlight this. Now, the way how I can take it is, I have a daughter. When she was one or 1.5 year old, I was training her to find the differences between apple, banana, and orange. In the first instance, she doesn't know what is apple, she doesn't know what is orange, she doesn't know what is banana. No. Slowly, I'll show her the red color fruit, which has a different shape, is called as apple. Second time, I'll show you the long fruit, which is in different color, is called as banana. And third time, I'll show the fruit which is in orange color, different shape, is called as orange. Now, first day, she will look at the colors and understand, okay, my dad is trying to tell me something. This might be orange, this might be apple, this might be banana. Slowly she gets familiarized with that one. And next time in a fruit bowl, if I put banana, orange, and apple, she will go and take apple because she likes apple and she knows it's apple. Okay, that is the normal data which you already labeled now. You labeled a round fruit as orange. You labeled a fruit with kind of round but not round as apple, and you labeled a long fruit as banana. This is how she understands it. She learned from it. Now, we have into guest house, guest place. In the kitchen, guest has a big fruit bowl. In the fruit bowl, they have grapes, they have oranges, they have apples, they have bananas, they have kiwi, they have strawberry, a lot. Now, what happens when my daughter sees the fruit fruit bowl? She comfortably can point apple, orange, and banana, but she's confused a lot with strawberry, grapes, and other fruits. Now, as your mind is already trained, you are able to distinguish between apple, banana, and orange. As you were never known or told or trained with examples on strawberry and grapes, you couldn't find it. Now, strawberry, grapes are the noise here. Apple, banana, and orange are the training set here. The reason why we always talk noise, train versus test is on your training data, you are already making sure that your algorithm knows about the labels. Labels is nothing but the class. Apple is one class, banana is one class, and orange is one class. When I'm aware of the classes, next time when you run the model on this model, I have already been aware of it, I was taught about it, and I also memorized about it. No. If you run the same model on apple, banana, orange, strawberry, and grapes, I can see strawberry and grapes which are totally new. So what happened? I have to again familiarize and make myself comfortable. That is the reason why the results what you see in apple, banana, and orange, and the time taken for a model to run and complete on apple, orange, banana, strawberry, and grapes are different. So whenever you get a random data adding to an existing data, that is called a noise. The reason when we are experimenting something, we do it with noise data. because when you do it with noise data, the data keeps changing. When data is keeps changing and if you run the same model, your model prediction should be always right. If that is the case, then you have chosen the right model. Okay, that is what it is. Are you clear till this point? Do you understand why I mean noise? Everyone?
Yeah.
Perfect. So first generate some linear data based on the quadratic equation. Now that is the quadratic equation. As I told you, x squared minus x minus 2 as shown in diagram. But here what I'm saying is ax squared plus bx plus c plus some Gaussian noise. Gaussian noise is nothing but your random data and random initialization. Now, for example, let's take m equal to 100. You have 100 iterations and my features is 6 into np.random.rand. Everyone in this class know what is np.random.rand. np is numpy, dot random is a function, dot rand is a class, m dot 1 is nothing but take from 1 to 100 and show me get me the random data. Minus 3. Minus 3 is again I'm telling my uh, features to use the random permutations and combinations and give me the data. Now y is equal to 0.5 into ax plus b plus Gaussian noise. Now 0.5 is a, okay, and 1 into x1, which is nothing but x square, 0.5 into x square plus x plus 2. The formula is simply taken there, implemented there. Now, when you're talking about polynomial regression, simply use Scikit-learn's polynomial regression class. Use polynomial features to transform the training data. Perfect. Add squares of each features in the training set as new features. Perfect. New features is equal to existing features in the training set plus square of each feature in the training set. This is the important implementation you need to understand. Again, guys, use polynomial feature class to transform the training data. As simple as it explains. Add square of each feature in the training set as new features. Now, what is your features? X. What is X? Random data. What is random data from 1 to 100? Now, this 1 to 100 features, add square of each feature. When I say add square, it doesn't mean 2 is 4. It means 4 is 2. 9 is 3. Okay. 2 square is 4, 3 square is 9, 4 square is 16. Like that. If you have 16 in your random data, it takes 4 as that element. If you have 25 in your random data, it takes 5 as a reference element for that. That's the implementation of it. Now, adding squares is nothing but if you have, for example, take you have 4, 9, 16. When you have 4, 9, and 16, your polynomial regression will take a reference number of 2, 3, and 4 and sum it up. When it is summing up, the new features, the 2, 3, 4 will be the new features. Now, the new features equal to existing features in the training set plus the square of each feature in the training set. So there's nothing but 2, 3, 4. 2 square is 4, 3 square is 6, 4 square is 16. So this is how it internally under the hood performs a mathematical calculation and gives you the result. Okay, look at the diagram. There is nothing yet, but we'll have to just observe what happens in the diagram. Okay, it has actually went like this. This is also gone like this. There's only one line anyhow. If I draw a line here, I'll understand what I'm trying to explain. But let's do it practically. Now, see here. Now import scikit-learn dot processing.import polynomial regression, first step. Second step, your poly features is nothing but polynomial features, degree, bias, and fit and transform. You got an array. Again, if you say understand the difference, first I did x of 0. Again, I did of x underscore poly. X underscore poly is the polynomial regression. X of the 0 is the result of the weighted or added powers to the existing features. That existing features are treated as new features. Now, if you are not comfortable on how to use the syntax, do not worry at all. As I told you always, just simply go to Google and say polynomial regression syntax. This is an awesome learning resource for data scientists towards datascience.com. You check anything about data science, that's the first page you will get because the number of hits to that page is very high, and there are a lot of great amazing contributors contributing to that. See, this guy used y equal to x minus 2.5 and I used x. Okay, simply simply applying a linear regression to the model to this data set. He has not he has taken one step ahead. We used simply scikit-learn and implemented it. The plot of baseline is like this, and RMSE and R2. You know what is RMSE? Not worry. Don't get scared when you see this kind of long quotes. That is very simple. From this one, he extended this to one level up. We will get there slowly when we do the whole real-time project. Okay. Now, this is how you can actually do second degree polynomial regression, third degree polynomial regression, 10th degree polynomial regression, which I'm going to talk later. The reason why I brought you here is if you have any doubt how the model works, just spend an extra minute on the syntax of it. Okay, now I'll say scikit-learn because I wanted to show you the syntax. Yeah, polynomial features. So this generates a polynomial and interaction features. Generate a new feature matrix consisting of all polynomial combinations of the features with degree less than or equal to specified degree. Now, what is the degree? The degree is nothing but the existing artifacts of your features are modified to the new weights. That new weights are treated as new features. That is what it is. Take an example. If an input sample is two-dimensional in the form of a comma b, the degree 2 polynomial features will be 1 comma a comma b, a square ab b square, or it can be 1 comma a comma b, a square ba or b square, or it can be other way around as well. So polynomial regression is simple. Take an input sample in two-dimensional and it has a comma b. Now the degree 2 polynomial features will have 1ab, a square, ab, b square, which means your a and b are multiplied, your a is squared, your b is squared. Like this, if you have a two-dimension in the form of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, your 10 will be multiplied 1 square, 2 square, 3 square, 4 square, 5 square till 10 square. That is 10 degree polynomial regression. What is the fun of doing it is what we are learning today. And what is the difference between each one, when to use which one is what we are going to use today. Okay, now look at the result. When I said x of 0, I got 1.24. When I get x poly of 0, I got 1.24 and also 1.56. This explains that this will be the revised weight of the new features on the linear regression applied to the nonlinear data. Okay, let's deep dive on this. Guys, are you clear on this one? Everyone, are you clear? Hello, are you clear? Perfect. That's good. How many of I got today? Ram, Kavi, Kishore. Okay, cool. Srisha didn't come, I believe, today. Okay, that's fine. Now, look at this diagram. N plus D exclamatory divided by D and N. Now, what is D and what is N? Simple, boss. Polynomial features with degrees equal to D. This means it transforms an array containing n features into an array containing features mentioned in the diagram. Now, once again, if you have 10 degrees, an array with 10 features will be converted into n plus d exclamatory divided by n exclamatory d exclamatory. If you ask me what exclamatory in n plus d, even I don't know, because I don't really care what the calculus does. All I care is, do I understand how it is implemented? That's all I care. Okay, now the polynomial regression is capable of finding the relationship between the features. Very good, simple statement. In this one, the plain regression model cannot do, because you are working one step ahead of linear regression. If there is a linear relationship, only then you use linear regression. If you're working on nonlinear data, you still wanted to find the relationship, you need to find polynomial regression, so it can find relationships for you. The reason why polynomial regression can do that for you is it adds all the combinations of features. That's what I just explained to you in scikit-learn polynomial regression features. When you have two-dimensional features of AB, it does a square comma AB comma B square. Just put that as reference. Now, if you again up to that given degree, when I say up to that given degree, if you are 2 degrees, it's a square comma AB comma B square. If it is 10, then it has to do 10 multiplication of 10 features and then the square of those 10 features. Now, for example, if there are two features a comma b, the polynomial features degree 3 will add these features also. So it's nothing but a square, b square, a3 and b3. It's not a3, it's a cube and b cube. It also does ab comma a square b and ab square. Okay, that's what it is. But remember, at least one of the feature have to be squared. At least one of the feature must be squared. Don't worry much about the formal implementation. You just need to have some information about it. That is the reason we are trying to learn this. Okay, I'm really waiting to help you all on my recent data science interview that happened on Tuesday. I thought to tell you yesterday, but you guys, some of you have not come up. So I thought it's not good when we have few attendance. We'll discuss over the weekend. Now, fitting a linear model. Now fit a linear regression model to this extended training data. We'll compare the linear regression versus logistic regression. Okay. Sorry, polynomial regression. Perfect. Simple boss. Here what I'm doing is I'm creating a variable called lean_reg, and I'm using my linear regression model. I'm fitting it on my x_poly. Again, x_poly is my extended training data. X_poly means you're adding weights to the existing data. When you added weights or when you are increasing the weights, that new weights are treated as new data sets. Perfect. My y is like that. Now linear regression dot intercept and linear regression coefficients. This is what I'm going to check now. Look at the model estimations. For example, here if I have got an output like this, my output here is this one. Okay, but the way model estimation works is y is equal to ax square plus bx plus c. Okay, now 0.56 is my a, 0.93 is my b, and 1.978 is c. Considering that example, I can use this one as my a, this one as my b, this one as my c. Now you should question me, Amar, why this is in one single array and why these two are in one single array? Because what happens is this one is an intercept and this one is a coefficient. I have very clearly explained you what are coefficients when we dealt with the first use case. Okay, if you're not aware of it, ask me now. I'll recap that. Are you clear with this diagram? Did you understand what I'm talking about? If you're not clear, just let me know. Guys, you understood clearly about polynomial regression. On the same extended data with the name poly_new, you are running a linear regression on that to see the differences. Okay, to see what is the difference between linear regression and polynomial regression. Are you all on same page? How many of you are with me? Perfect, that's good. 59. Learning curves. Guys, this is very important. When I say learning curves, always remember you are at the top of the hill and you are trying a way to reach to the bottom of the hill. Again, you are at top of the hill and you are trying to reach the bottom of the hill. You may have a lot of questions. How can I go down? And you think if I take slow steps, it would be easy, so I won't fall down. Or you might think I'll just roll down scribbling. Or you might think I'll turn east and see how it would be easy for me to go there. Or you'll still think, let me take a north and still see how I can go there. These are all the assumptions. Now, if you are at that top of the mountain every day for some work, and by the time you finish the work, it's so dark and you have to come down. Every day you come down, but every day is a learning stuff for you. You learn something every day, right? One day you find a rock, and next day if you come in that direction, you will be careful that yesterday I found a rock here. Let me be very careful. And some other day in the dark, you may fell into a pitfall, and you will learn from it. And the following day, you won't fall into pitfall because you know there's a pitfall. So first day you found a stone, second day you found a pitfall, and third day you might actually find a better route than what you found in first day and second day. What is this? This is learning. How are you learning? You are learning it from your experience. You are learning from what happened to you in the journey. Now, that is called learning curve. Let's implement this learning curve on 1-degree polynomial regression, 2-degree polynomial regression, and 300-degree polynomial regression. Okay. Now, as we have seen earlier, high-degree polynomial regression fits the training data much better than the plain linear regression. This is one mistake. I have to correct the slide. Let me give you 1 second. This kind of things will happen. Erase all the drawings. Go back to the pointer. I don't know, it's not working. That's fine. Now, see, high degree polynomial regression fits the training data much better than the plain linear regression. Again, what is high degree polynomial regression? Checking with 1 degree, checking with 2 degrees, checking with 300 degrees. When I say 2 degrees, it's a square, comma ab, comma b square. When I say 300 degree, then multiplication of 300 features with square of 300 square of features. Perfect. Now, when your polynomial regression can do better than plain regression model, let's test it. Now, let's look at the fit of plain regression model, second degree polynomial regression model, and 300-degree polynomial regression model. Okay, perfect. Let me come back to here. Let me show you here. Now, the plain regression model is red color. This is y equal to mx plus c, the line of graph. We know about this one. Second polynomial regression is in blue color. What is blue here? This bit. Let me change the color, guys, for everyone's benefit. Blue color. This one is second one. Okay. The dark blue is 300 degrees. So I'll take dark blue. Or do I have that? I'll take green. Okay. This is 300-degree polynomial regression. Now, we need to observe something from it and we need to learn from it. Okay. Now, your linear regression is straight. Okay. What do you understand this in the straight? The only thing you understand is few records I have on the top, few records I have on the bottom. I'll try to judge this is the expected, this is the actual data, or this is the predicted data, and this is the actual data. This is the predicted data, this is the actual data. This is how I check the comparisons and check the linear regression. Now, the beauty of having the multi high degree polynomial regression is your data is going very, very close. Now see, this graph, okay, guys, 1 second. This graph is good or this graph is good. Tell me something. This is the intersection area for all the three models, but this is not going, the red color one linear regression is not going as close as the predicted values. It is taking you to the nearest point of the predicted values and left it there. But what is the second degree polynomial doing? It has taken you much closer to the predicted data. Okay, predictions. Now, take about 100, 300 degree polynomial regression. This is quite awesome than that one because it is touching each and every thing. See, these dots are the data points. Look at your model. See how it is touching. It's touching almost all the things and giving you the result. Now, why is it so bumpy here? When I say bumpy, why is it so much randomized there? Because of the Gaussian noise or the noise we intentionally created. Okay, this is the differences between second degree, third degree, or 300-degree and comparison with plain regression model. Let's go to next slide. All clear till this point? Everyone happy? Did I start the recording? Yeah, I started it. No problem. Screen is shared. Yes, it's shared. Perfect. All clear till this point, everyone? Perfect. I'm happy. Cool. Let's go to the next slide. Now, learning curves continuation. Now, as we saw in the previous diagram, in 300 degrees polynomial model, it wiggles around to get as close as possible to the training instances. We observed that. Super. Amazing. It is very clear that the high degree polynomial regression model is severely overfitting the training data. The linear model is underfitting the data. This is what we are trying to come up with. If you have asked in an interview, Amarnath, I have a linear data, I want you to establish a relationship. Simple, boss. I'll use linear regression. And if he asks you, why not use polynomial regression? Just tell him, boss, polynomial regression has the benefit of establishing a relationship between nonlinear data as well. But the problem is, at times, in your noisy data, the high degree polynomial regression model is severely overfitting the training data, and the linear model is underfitting the data. That's what it is. Simple. How do we find if a model is overfitting or underfitting the training data? Now, we have already talked about cross validation. We also implemented n-fold cross validation. We also implemented threefold cross validation in using scotatic gradient descent and also some other models, also some other attribute combinations also. Now, this slide is done. So you need to know how to find a model is overfitting or underfitting the training data. Now, if a model is performing well on a training data, but generalizes poorly according to the cross validation, then it is overfitting in case the model is too complex. If a model is performing poorly on both training data and cross validation data, then the model is underfitting. In this case, model is too simple. Other way of understanding this one is, if your model is generalizing the contents very easily, if your model is just giving you results so comfortably, and it is performing poorly on both training and cross validations, then it is underfitting. If your model is performing well on training data and generalizes poorly on cross validation data, again, when I say this, go back to my daughter's example, apple, banana, orange versus apple, banana, orange, strawberry, grapes. Okay, now if a model is not doing well on the new added features, or to that matter, if it's not doing good on the validation data, then that is called overfitting. This is also understood. Let's go to next slide. Now, another approach to learning curves is, learning curves are nothing but they are plots of the model's performance. Learning curves are the training set and the curve that is implemented on the training set and validation set. This is the function of training the set size. We understood that. To generate the plots, simply train the model several times on different size subsets of the training set. Done. Learning curves of the plane regression model. We need to plot the learning curves. We'll train the model on different subset of the training curves, and we plot the root mean square error and the training set size. Okay, this is what it is. Another approach to look at the learning curves. Actually, your learning curves will give you a clear picture on where you are directed and how you are going to get the results. But while implementing the learning curves, you need to know a few touch points and data points. That touch points is nothing but how you can plot the root mean square error and how you can further break down your model into subsets and train on different sets of subsets. Okay, generate a plot and compare the plots. Perfect. Look at my diagram. My red color is in training data and my blue color is in validation data. How is my training data doing? How is my validation data doing? Okay, let's come to the other diagram here. Look at this. Guys, look at the first diagram on my right side. I have highlighted a point 0, comma 0. Second, I have highlighted the right side 1, and third diagram I have highlighted the curve that is between 1 and 1.5. Now, when there are just one or two instances in the training set, the model can fit them perfectly, which is why the curve starts at 0. Done. If we have one or two instances, it starts from 0. If you have more features, if you have more instances, then things may change. I'm saying things may change now. But as a new instances are added to training set, it becomes impossible for the model to fit the training data, because both cases the data will be noisy and they will be not linear at all. Perfect. The error on the training data goes up until it reaches a plateau. Again, you know what is a plateau. At that point, adding new instances to the training set doesn't make the error, but it makes it worse. When the method is trained on few training instances, it is capable of generalizing properly, which is why the validation error is initially quite big. Look at the diagrams and relate my statements. You understand what I mean. And if you have not understood, I can repeat it. One thing we are trying to make here is, if you have two or three instances, it's straightforward, boss. You can clearly establish a relationship and you can plot the diagram and the curve will start at 0. Straightforward. But what happens when you go on adding new instances? Again, what happens when I'm adding a new instance? I have apple, banana, orange, which I already know. Now you are adding grapes and strawberries. I have to get trained what is strawberry. I have to get trained what is grapes. Again, I have to work with 5 of them together. There is a noise there. Initially, there is no relationship between 5. That's the reason I won't find it. Once I familiarize the relationship between 5, I may do well. That is the importance of adding new features to that, adding new instances. I'm sorry, I don't mean to confuse you. It's adding new instances, not adding features. When I say features, it is like your data set points, your columns, I would say. Now, in this process, when adding a new instances to the existing training set, the errors on training set data goes up until it reaches a plateau. Look at the diagram on the right side in the second one. Now, it doesn't make the error much better or worse. When the model is trained on very few training instances, actually, it is incapable of generalizing properly, which is why the validation error is initially quite big. Are you clear with this explanation? Everyone, look at the diagram. It started at 0, and right side the red color is highlighted, and on the left side between 0 and 0.1 and 1.5, that is nothing but the validation error, I would say. Okay, go to next diagram. Now look at this one. In this one, as the model is shown more training examples, it learns and thus the validation error goes down slowly. What I mean is the way you trained me on apple, oranges and banana, if you can train me on grapes and strawberries also, I can do well. That is what it is telling. A model is shown more training examples. More training examples, more experience. More experience, more learnings. More learnings, machine learns well. When machine learns well, the validation errors comes down. Now, since straight line cannot do a good job modeling the data, the errors ends up at the plateau. Look at the difference between last diagram and this diagram. Now I'm talking about blue line, which is validation data. Okay, look at the diagram below, the blue color line and the red color line and the highlighted part. Now this is very close to the other curve because we have properly trained it on more training examples. That's the importance of it. Slowly you're getting it. You need to re-establish everything with a pen and a paper. Have a whiteboard session within yourself. Look at the diagrams. Make a note of what I have been discussing with you. I think the slides are looking more beautiful than what we did earlier. Earlier we used to have more theory. Now we are having theory plus implementation plus plots explaining how we work. Now, this one, learning curve tip. What is the learning curve tip? Tip is nothing but it makes your life easy. These learning curves are examples of an underfitting model. Perfect. Both curves have reached a plateau. I've observed it. They are close and RMSE is fairly high. Yes, when RMSE is high, that means errors are high. When I say errors are high, they have reached a plateau. Now, if the model is underfitting the training data, then adding more training data will not help. That is for sure. This weekend, this is what I'm going to explain you. This weekend, I'm going to explain few logical interview questions that is coming up. First, I'll ask each and every one of you, answer me this question. I'll get an answer from you and I'll explain you properly. Now, we need to use a more complex model or come up with better features when you have underfitting data. Just remember, if you get underfitting data, don't just go and add more training data. Rather, use a complex model or come up with better features. Next diagram. Look at this one. Let's plot the learning curves of a 10th degree polynomial model on same data. When I say same data, x underscore poly, which is a added weights of your existing features. Now get an observations from it. If you see it carefully, the error of the training data is at 0.5, which is much lower than the linear regression model. 1.5 is less than 2. Okay. What I'm referring here is, if you are confused, this bit, this line here, and observe carefully. Observe carefully. Here, what we are going to talk is, we are establishing the relationship between this one and this one. This is linear regression versus polynomial regression. No, we are plotting the 10th degree polynomial regression. The error on the training data is 0.5, is much lower than with the linear regression model, which is between 1.5 and 2. Okay. Again, the gap between the curves is, this means the model performs significantly better on the training data than the validation data, which shows the model is overfitting the training set. Again, we are talking about overfitting. Just 1 minute back, we spoke about underfitting. Theoretically, when we speak underfitting, but practically the data is overfitting. How can we sort this one? We'll talk tomorrow. Okay. Today we covered concretely the polynomial regression and we just started the learning curves. And I'll spend some time today and I'll prepare the slides tomorrow and we can finish the rest of the concepts. I'll try to finish the rest of the concept tomorrow. For some reason, if I don't make it, we'll take one more session and close it off. Guys, I need your feedback. Seriously, you are at the edge now. If you don't open up with your concerns, if you don't open up with your problems, if you don't open up with the way you're catching up with my concepts and revising them, then it's a loss for you and not me. So when we have workshop on Saturday, guys, one more thing, Saturday and Sunday, please, I'm not against your personal commitments. If you have personal commitments, please go ahead, no compulsion. But I want you guys to come Saturday and Sunday also, because we are at the edge now. We just need to work hard a bit more. I thought to finish within 3 months, but the Python itself took totally 14 classes, continuous stretch 14 classes, because I have covered everything in Python without leaving any single bit. I know one last thing, scikit-learn is pending in Python, which we can complete. It took a little more time than expected. As I told you on the day one itself, as is the first batch, we learn from the experiment. So I'm also learning. The second batch and all will be concrete on the timings, implementation, concepts, and everything. You need to please excuse me and forgive me for that. I'll see you all tomorrow. Thank you so much for joining me this morning. Please be prepared and come for the workshop on Saturday and Sunday. Saturday we'll have facial recognition and also interview strategies and implementations. Sunday we'll have one more use case where we can work together on one of the real-time use case. Okay. Thank you so much. I appreciate your time. See you all tomorrow. I'll record the video shortly and come back to you. Thank you so much. Thanks, guys.